Okay, one of the things that, of course, we have to go back to and discuss is the quantitative applications of fluorescence versus absorbance. Both of these processes refer to electronic transitions, where we're going from one state to another state, where we're changing the orbital description. Both of these can be used for quantitative measurements. We already know that. The amount of light that is absorbed by a mixture is going to be linearly dependent upon its concentration. So the more molecules we have, the more the light that is going to be absorbed by the species. That gives rise to the Beers-Lampert law. But it also makes sense that the more species that you have in the excited state, the higher the concentration, the more the fluorescence. So really, the Beer-Lampert law works perfectly if you're talking about emission or absorbance. Fluorescence versus absorbance. Both can be used in Beer's law for quantitative analysis. The key is, what is the difference between them? And we have to just look, again, really briefly at a basic block diagram of how these species are done. So in absorbance, what you do is you have a source, and the source puts out radiation, which you select a wavelength, and you observe how much light is there initially, and then if you put the sample in the way, how much light is absorbed by the sample. This gives rise to percent transmission with the compound in place, or how much light is absorbed. It's really a relative amount of light that is going to be absorbed, and this has to be done by looking at the sample directly in line with the source. What you're looking for is how much of this light is being absorbed by the sample. That seems pretty straightforward. Fluorescence, the source has a different purpose. See, in fluorescence, what you want to do is just observe how much light is being emitted. So the purpose of the source in a fluorescence experiment is really just to populate the excited state. The only purpose of the source in fluorescence is to put everything into the excited state. And then, a few microseconds later, it's going to fluoresce. In absorbance, you compare how much light gets through to how much light is absorbed. In fluorescence, You're really just counting the number of photons that are being fluoresced. You're not interested. The source can be absorbed, some of it, little of it, doesn't matter. All you care is that you put a lot of the sample into the excited state so it can fluoresce. Then count up the number of fluoresced photons. This gives rise to a difference in geometry. See, because if we put our detector here, and let's say we used the sun as an excitation source, and we're looking right at the sun. If we are in line with the sun, and a few of these little red photons are being emitted, I'm guessing that staring at the source is not going to help our dynamic range problem. So in fluorescence, what you can do is change the detector to 90 degrees away from the axis of the excitation. The reason this is important is pretty obvious. All of the source light that is being used to excite the sample is going to go straight through. Most of it won't be absorbed. And if we had a sensitive detector sitting over here, it would be blinded, meaning we would go beyond the dynamic range and the sensitivity would not be there to detect the few photons that are going to be fluoresced. However, if we move the detector to 90 degrees, the photons from the fluorescence, which are going to be given off in any direction, can now go down and be seen by the detector. This way, the detector never has to differentiate between the sample's fluorescence and the source's intensity. In this way, fluorescence can use a highly sensitive detector. It only needs to detect the 1 or 2 photons that are being detected. There's nothing else going to create signal other than the fluoresced photons. So it doesn't have to differentiate. So the transducer, the detector, here, located at 90 degrees to the excitation, can be extremely sensitive, as opposed to an absorbance detector, which needs a really high dynamic range because it has to differentiate between the source and what the source looks like after some of it has been absorbed. This detector in absorbance needs high dynamic range, which means low sensitivity, as opposed to fluorescence, which can use a high sensitivity detector with low dynamic range, because it doesn't have to differentiate between the source output. All it has to do is count the photons that are being fluoresced. This means if you're looking at absorbance versus fluorescence, absorbance has high dynamic range because of its geometry. It has high applicability because everything absorbs, so you can use it for pretty much everything. It has low selectivity because, like I said, everything absorbs. Fluorescence, on the other hand, has high sensitivity only because of its geometry of where the detector is relative to the source. And it uses a high sensitivity detector. It has high selectivity because not everything fluoresces, but it lacks the broad applicability of absorbance because not everything fluoresces. You can't use it for everything. Both of these techniques, absorbance and fluorescence, are used predominantly for quantitative measurements, meaning Beer's law. And the differences between them is absorbance is broadly applicable with big dynamic range, but fluorescence is highly selective with incredibly high sensitivity. Even though it's a low probability event relative to absorbance, it still has very high sensitivity because we can use a very sensitive detector.